Okay, so my name is Andrea Melloncelli. I'm a physicist. I'm a senior data and AI scientist. I co-founded Apply Quantum. So Apply is a company that aims to develop and commercialize innovative solutions based on mathematical models and artificial intelligence. And we provide tailored training programs for C-level executive, technical people on artificial intelligence and quantum computing. Relating to the latest, we focus on its principle, current capabilities, and strategic implication for business. Our goal is to equip decision makers with the knowledge needed to evaluate the potential impact of quantum technology on their industry and tech people with the latest tools and methodologies. Here our set of training courses. So about Python, we start with data analysis and reporting with Python. So we start from scratch and we train people to do analysis and create reports and dashboard with Python. Then we have a course on data science, basically machine learning topics. Professional project management with Python. With this course, we teach how to bring solution into production and to create value for the business. You can see this course as a professional data engineering course. We have quite big course on deep learning and generative models. We start with dense neural network. We see convolutional neural network, recurrent neural network, until we see together the usage of pre-trained Hugging Face model like NLP, visual, or large language models, and their fine-tuning on data, on your data. Then in this course, mastering large language models with AI agent, we teach how to prepare and use a large language model to create agentic application using no-code software, but also with Python with LangChain framework. This is the part on quantum. We have a number of courses in statistics, starting from the foundations, statistical quality analysis, factorial designs, response surface designs, design of experiment, formulation and mixture design, statistical modeling, introduction to reliability, advanced reliability, and analysis of normal data. And we are searching for people. So in case you are interested, we can have a conversation later. So let's come back after the advertising to our topic. Let's talk about quantum computing. So today's agenda is starting with a little bit of quantum technology. And then we will see how to program a quantum computer. We see a little bit of theory. We see how to code a quantum circuit. And we see some real example running our circuit on a real quantum computer. Okay, so let's start with quantum technology. Quantum technology refers to the technologies based on the principle of quantum mechanics, which is a branch of physics that models and describes the behavior of atomic and subatomic particles. And unlike the classical physics, which governs macroscopic phenomena, quantum mechanics captures the counterintuitive and probabilistic nature of the matter and the energy at the smallest scales. There are mainly three subfields in this sector. Quantum computing, which is the new paradigm of computer, which leverage the laws of quantum mechanics, something that we will talk about today. Quantum sensing, which includes a new generation of sensors that are order of magnitude more sensitive than the classical sensors, and quantum communication, which is basically the new internet, the technology on which the new internet will be based to secure the transfer of information across distances with the quantum technology. So we'd like to start talking about what is a quantum computer, what kind of processes can speed up, and etc. So let's start with a physical experiment, the double slit experiment. On the left-hand side of the figure, you see the emitter of particles. Okay, in the middle you see an armor, so basically a wall with two slits, two holes. And on the right-hand side, you see the screen that records the particles that arrive to the other side. So basically, this experiment prove that particles don't pass through the slits on the left or the slit on the right. The shape of the figure that you have on the screen prove that particles pass through both slides. A single particle passes to both slits at the same time. And this is due to the nature, to the wave nature of the quantum particles. And they behave in this way. And one proof of this is that if you close the left slit and let the right slit open, you see a figure on the screen. If you close the right-hand side and you leave the left-hand side open, you see a similar figure on the screen. And you would expect that if you open both slits, you would see this, the sum of the two figures on the screen. This don't happen. The figure is completely different. This is because the particles passing in the two slits interfere each other. Okay? Okay, and okay, but let's talk about what happened in a quantum computer. In a classical computer, we have two possible states of a classical bit: 0 or 1. 0 if there is no current, 1 if there is current. Okay, 8-bit make a byte, 1024 byte make a kilobyte, and so on. If we look at a qubit, which in this slide is represented on the right-hand side as a sphere, all the points of the sphere are accessible states. Okay, so there is a huge degree of freedom in representing the information. And later we will see how this works. Just an example to see how much information a quantum computer can handle is related to the molecule of caffeine. So basically, the molecule of caffeine has a lot of states available, energetic states available. So in order to describe the energetic state of a molecule of caffeine, you should use 10 to the 48 classical bits. So a 1 with 48 zeros, okay, which is a huge number. How much huge? Just to make a comparison, 10 to the power of 50 is the number of atoms on the planet Earth. Okay, so you're not going to make such a computer. But with the 160 theoretical qubits, you can represent all these states just with 160 qubits. Okay, here are some references where to start, and we will start today with working around with the Qiskit, which is a library from IBM, which allows us to use to create quantum circuits and to run them on a simulator and on a real quantum computer. I need to change my slides. I have two of them. Okay. Okay, so let's start understanding a little bit more. Let's start from the classical information. Okay, so let's start giving a new notation from the classical bit. So a physical classical bit is a binary, because it can assume 1 or 0, two values, deterministic variables, meaning that if you set your bit to be in 0, at the moment of measure, so when the computer, puts the value 0 in the memory, and when it goes and reads the value, it reads 0. Okay, so this notation means that the probability for the bit in the state 0 to be measured as 0, let me see, okay, here is 1, which means 100%. The probability to measure it as 1 is 0, because it has been set to 0. Okay, so there is no possibility that you measure something different. There is a tiny possibility, but it's negligible. Okay, so let's give a vector representation of this this concept. In here, we see the vector representation of this deterministic state of the bit. Okay, so 1 means 100%, 0 means 0%. The fact that the 1 is in the first position, in the position of 0, remember how Python arrays work, okay, the first position is 0, so we have 100% that this bit is read as 0, and 0% that the bit is read 1. But let's do let's try to imagine if this bit is not deterministic, but probabilistic. So let's pretend, for example, that the probability to measure 0 is 3/4, so 75%. And the probability to measure 1 is 1/4, 25%. Of course, the sum of the two is 100%. Okay, there is no other option, or 0 or 1. And we write the state in this way. So 3/4 and 1/4. The vector must be normalized, meaning that the sum of the two is 1. Okay, and again, physicists have another notation for this state, but when you want to study quantum computers, these are the basics. So they still work with a ground on the quantum physics. And this is the same notation physicists use to represent particles. And this is the Dirac notation. Here we have B, okay? The column vector B, the pipe B, and the right angle parenthesis means column vector. Some other can call it ket, okay? So it's a ket or it's a column vector. Is equal to 3/4 0 plus 1/4 1, okay? If we define 0 in this way, so the base state 0, and this is the base state 1, when we do this linear combination, we get back exactly 3/4 and 1/4. Okay, so basically, this starting makes sense, right? So we have two base states, two deterministic states, and if we combine linearly these two states, we get a probabilistic state. So again, what this means, it means that if we measure B, 75% of times we measure 0. Yeah.
Do you have to square the amplitudes before you have them? Do you have to square the amplitudes? Or
Okay, you are right for quantum, but here it's not quantum, is still classical probabilistic bit. So the definition is that the numbers are just the probabilities. Okay, I started in this way to make it, trying to make it simpler. Okay, and after this, okay, so 75% of chance of measuring 0, 25% chance to measure 1. And after the measurement, the state of the bit will change. So basically, if we measure, we have this bit, right? When we measure it, if we measure 0, the state became the ket 0, okay, so 1, 0. And if we measure 1, the state became 1. Okay, now that we have seen vectors, we can look at the representation of operators. So any function that we can apply to change the states are linear operators, which means they are matrices. Okay? So if the state is a column vector of size 2, the matrix is 2 by 2 matrix. Okay, now let's see the real quantum notation. So a quantum state is very similar to the classical probabilistic state, but it has complex coefficients, okay? Meaning that in this case, alpha 0 and alpha 1 are complex numbers. But again, 0 and 1 are the basis states, okay? Okay, and alpha 0 and alpha 1 are called amplitudes, okay? So they are not probabilities, they are called amplitudes. Let's look at the single qubit. So this is the representation of its state. As our colleague stated, the probability to measure the state 0 now is alpha 0 squared. And the probability to measure the state 1 is alpha 1 squared. Okay? So the sum of the two probability must be 100%. So the sum of the alpha squared, alpha I squared must be equal to 1. This is a normalization constraint. Okay, and these are two example states. Let's take the first one, just to do some math with it. So with this state, the probability to measure 0 is the first coefficient squared, which is 1/2. Okay, so we have, in this case, 50% probability to measure 0. And of course, 50% probability to measure 1. Make sense? Okay, let's look at the 2-qubit system states. Okay, we had a basis with 0 and 1 with a single qubit. Now we have 2 qubits. We have 4 base states. One is 0, 0, so the deterministic state in which all the 2 qubits, when measured, return 0. 1, 1, the deterministic state in which the measure return 1, 1, and the same for 1, 0 and 0, 1. Where, if you want to have some notation, this is the notation that from 2 separate qubits build 0, 0, and etc. And so this is the state, the representation of the state of the 2-qubit system.
So, do you mind explaining that notation? Just because, what is that? What is that product meant to denote?
It simply means that if you have a vector of dimension 2, and this, if you remember, is 1, 0. This is 1, 0. This vector is 1, 0, 1, 0, a column vector of dimension 4. Okay? Okay, so, and this state can represent all the states, all the possible state of the system of the 2 qubits. Okay? But the point is that I cannot choose, okay, I have the constraint of the normalization. So alpha 0, 0 squared plus alpha 0, 1 squared plus alpha 1, 0 squared plus alpha 1, 1 squared is equal to 1. Okay, 100%. That remains. But the point is that imagine that, so this notation does not take in account that the 2 qubits, if the 2 qubits are independent, they give 2 independent measures. I will explain it better. So let's start from here. Okay, we have 2 qubits, and we have the system state, which is psi. This is the first qubit, alpha 0, 0, A0, 0, A1, 1. And this is the other qubit. Okay? If we do the math, we get this, this set of coefficients. Okay? And this is very similar to the previous state. So imagine that we want that this coefficient is 0. This other coefficient is 0, and we sum the 2 states 0, 0, and 1, 1. Okay? If we do some math, we realize that if alpha 0, B0, the product is 0, one of the 2 must be 0, right? And the same for this. So as a consequence, you can see that also this and this are 0. Why is that? Because if you look at this state here, we are saying that in this case, So, for example, I measured the first of the 2 qubits, okay, and I found out that it is a 0. What is the state of the other? It should be random, right? Because the 2 qubits, I told you at the beginning, that are 2 random objects that when you measure, you have a probability to measure 0 or 1, okay, depending on its state. But if you look at this state of the system, if you measure 0 on the first qubit, the second must be 0 also. So we have 2 random number generator, but if I run the first one, I get the same number on the second one. So this is a peculiar state, okay? And this is an entangled state. In a while, I will explain what it is. So coming to the previous slide, if we have this notation, okay, we are in a product state. A product state, because it comes from the product of 2 independent states, the 2 qubits are independent each other. Okay? And so this condition holds. A alpha 0, 0 equals to A0, B0, the first one. If this condition does not hold, measuring 1 qubit influences the state of the other. So in particular, the entanglement is a quantum phenomenon that happens when you have a particular interaction with 2 particles. So the 2 particles have this interaction, and they are in a random state. The 2 particles can go away from each other, okay, but they are entangled. Okay, so when you measure 1, okay, the state of the other is determined. Okay, so if you measure 0, the other will be 0, and this is weird. There no exist a similar concept in the classical physics. Yeah.
In the equations that we showed before, where you assume that the particles are entangled, so where it's coming from? Because it's not like 2 random quantum particles taken into account. It's just like how you mathematically formulated that they was entangled from the beginning.
Okay, it wasn't approved. What I stated is that if you have, so I stated that any state of a system of 2 qubits can be written in this way.
Okay, as soon as you get the system, you get entanglement. But in order to get there, you need to create it.
Yes, yes. Exactly. And we will see how to create this state, for example, which is very simple. It's a couple of operations on a circuit, okay? So in this case, this particular state is not representable as 2 independent qubits, but a single 2-qubit state, okay? And these, the Bell states, are an example of it. We are getting to the practice, don't worry. Okay. Okay, do you remember the sphere I showed you before? Okay, it's this one. Okay, this is the block sphere. Okay, and all the point of the sphere are accessible states for a single qubit. Okay, so the north pole represented the state 0. The south pole probably is small, but represents the state 1. Okay, all the other points of the sphere are a superposition of the two states. Okay, so they are probabilistic states, and they are a linear combination of 0 and 1. So what happened if the qubit is in this state and we measure the value of the qubit? You probably remember that we have 100% to measure 0. And the bar plot on the right-hand side show exactly this one, 100% to be 0. This other state, you know, where the arrow is pointing to the south pole, is the situation in which when you measure the single qubit, you get 100% of times 1. Okay, fair enough. What happened here? Okay, now the point is on the equator. Okay, so we are on a superposition of states. 50% I will measure 0, 50% of time I will measure 1. So 50-50. Now, look at the arrow. Okay, now we are not anymore on the equator, we are in the north hemisphere, so it's still a superposition of two states, but not symmetrical, okay? And as a consequence, we have two different probabilities to measure 0 or to measure 1. Now, look at the arrow. Now, look at the arrow moves, okay? Is on the same parallel, okay, but it has rotated. And the two probability distributions, the probability distribution is the same, meaning that every point in the sphere on the same parallel provides the same distribution. Okay, so these two states are different, but the probability distribution is the same. So the difference between the two states is called phase. So they are two different states because the phase differs. Yes?
Sorry, maybe you're getting there, but what's the point of representing it as a sphere where all the points on the same parallel are equally likely versus just a line?
Because you can prove with all the math that I show you that the state of a single bit can be represented as the point on a sphere, and you see also these rules on the distribution probability, like that if you move the arrow, the state on a parallel, you have the same probability distribution. So it's as simple as one of the representation, the possible representations, the most used. Okay, let's start with 2 qubits. Okay, here we have a quantum circuit, and here we have nothing. Okay, we have 2 qubits, Q0 and Q1, okay, on the vertical, and on the horizontal axis you have the time. So the sequence of operations applied, and here there is no operation applied. Okay, so you see empty lines. So the initial state is usually initialized as 0, okay? And the output state is, of course, 0, 0. Because both of them are in the state 0, and when you measure, you are so sure that you will measure 0, 0. Okay? And this is the representation. So we have 2 qubits, independent qubits, in the state 0. Now, okay, and this is the probability. So the bar plot is similar, but here now we have the state of the system. Okay, not the state of a single qubit. And we have 100% to measure 0, 0. Now, we apply the first quantum gate, the Hadamard operator, the one with the H here. So basically, when you build a quantum circuit, you apply linear operation to the quantum state, okay? And depending on their function, they have some effects. The effect of the Hadamard gate, which is a single qubit gate, is to transform the state of the system in this state here. So, what can we say about this state? By the way, qubit 0, you find the qubit 0 here and here. And this is the qubit 1. So the number moves from the right to the left. So what can we say? So the probability is the squared of the amplitude. So here it is 1/2 and 1/2. So with 50% probability, we measure 0, 0. With 50% probability, we measure 0, 1. Okay? So the qubit 1, what will be the value of the qubit 1? Okay, here is 0, and here is 0. So it will be 0. Okay? And this is consistent with the fact that we didn't apply anything here. So it was in 0, it will be still in 0, even if the notation here is a bit weird. Okay? And we have 50% to measure the qubit 0 in 0 and 50% to measure the qubit 0 in 1. Yes, exactly. I cannot hear you. It's still? Exactly, exactly. It's still a product state. Exactly.
Sorry, why did you switch? The base split.
Possible 1 and not 1 0.
Why is it 0, 0, 1 and not 1, 0?
Because this is the notation. Simply because we find the qubit 0 here and the qubit 1 here.
Right, left.
But before it wasn't that case.
Yes, it was always the same.
This is important because afterwards the notation gets complicated, so I want to make sure, even though.
Okay. Yes. Yes. Sure.
Before we had the B, and the B had 1 in the 0 to the north. That this is 100% of the value of 0 and 0 in the array. Place 1 in the array to denote the 0%.
Okay. Okay.
That's
Probably.
classical. I know.
No. Okay. Okay. Probably. Don't confuse the two notations.
Here.
One is the column vector, but this is not a column vector.
No, I understand.
Okay.
This is a tensor. But the first state, the first of the qubits, is that in the cat? Is that the one closest to the right or to the left? Q0 is represented.
Oh, yes. Here you have a Q0. This is Q0.
Right, but in the cat, in the output.
In the
state.
cat is the second one, this one.
Right. So Q0 is the one closest to the cat, and then Q1, the notation. That's the notation.
That's a notation.
Write them like that.
Yes.
What's about in the views in the brass? Are they left to right? They're right to left in the caps, but what about in the brass?
But basically, there is no strong meaning in changing the two from left to right or to right to left. It's simply the notation that put here the first and then continue. So if you...
No, he's asking about the bra of the bracket. Is the notation left to right or left to left?
No, it's in the same order.
Same.
Okay, so as someone stated correctly, this is still a product state. So the two qubits are independent, okay? The 0 has 50-50%, 1 has 100% to being 0. Or you can read the thing differently. You have 1/2% to measure 0, 0, and 1/2% to measure 0, 1. But this is the same concept, okay? Okay, and this is the distribution. Okay, so we apply another operator here, which is a conditioned not operator. So basically, this inverts the value of Q1 provided the value of the other qubit. Okay, so this is the controlled one, and this is the one in which the action takes effect. Anyway, doesn't matter. The output state is this one. Okay, and if you remember, this is an entangled state, because if I measure the first one, I get the value of the second. If the first one is 0, the second one is 0. If I measure 1, the second one is 1. Okay, so this is an entangled state. What do you think will be the representation in the two Bloch spheres? It's a tricky question, and the answer is it's impossible to depict the state of a system with two independent Bloch spheres. So the Bloch spheres is a good representation for a single qubit or for some independent qubit, but not for a system. Okay. This is the distribution. 50%. How do you physically? Okay. Physically, it depends about the hardware, but the point is that this operation can be done on any quantum hardware. I mean, quantum computers working on gates. Okay, and the logic behind the operation is the one that you invert this value based on the value of the other. Okay, then how you do on the hardware depends on the hardware. And that is the difficult point in building a quantum hardware. Okay, not the difficult point, but you know, this is the work of the hardware builder. This is another notation, so don't confuse this with a Bloch sphere. This is a Q sphere, and this is a representation for a state of the system. Basically here it states that we have two possible states, 0, 0 or 1, 1. Okay, I tell you this because you see this representation many times, and at the beginning you may think, okay, this is a Bloch sphere. No. Okay, and this is an example of circuit. Okay, and now it's your time. So I prepared some notebooks, Jupyter notebooks on Colab, But the point is that I don't know exactly how to share with you the link. So, a Slack channel. Okay. Come on.
Official Slack channel where other people doing workshops.
Okay, I asked if there is any Discord channel, but that's why there is no Discord channel. I can. Okay, for me it's too late to create an account on the Slack and to be accepted on the Slack. I may share this with a QR code, and then if some of you can share it on the Slack channel, it's a great thing. Okay, now share. QR code generation. Okay, this is the link. It's a Google Drive folder with 4 notebooks. If someone that shared the link on the channel, tell me on which channel is so that I can.
It is the tutorials channel.
Okay, on the tutorial channel. Tutorials. Okay, thank you. Thank you very much. Okay. Just main display. Okay. Can you read? Okay, tell me when you are ready. Did you find the link with the Google Drive folder? Okay. Okay, so so the notebook starts, of course, with the installation of Qiskit packages. Okay, by the way, Qiskit has a website where you find a lot of material, documentation, etc. Later I will show you the link of before, the link in the slides. Okay, and we install all Qiskit, included the visualization part, okay, to create the block sphere, etc. Then we have another package, which is Qiskit IBM Runtime. The goal of this package is to let you work on a real quantum computer. So to connect with the IBM cloud where quantum computers are there for you to execute jobs. And this Qiskit IR is the opposite of it. It's a package that contains the simulator. So when you want to simulate a quantum hardware, you use this package. When you want to connect to the real runtime, you need this other package. Okay, now I have installed both of them. And then you import these libraries. When you may go on the Qiskit IBM website and try some other exercises, remember to look at the version of these packages, okay? Because from a version to the other changes a lot. So if you want to reproduce an exercise, I strongly suggest you to install the precise version numbers.
Should be 100% reproducible, or it should be random in that sense?
No, it doesn't run. It ends up with some error because they change a lot the notations. Okay, then the second cell. Okay, try from Google Colab import user data just to know if we are on Colab or in another Jupyter notebook, and that will be useful for the last notebook where we will connect to the quantum hardware. For now, this is not really useful. Okay, third cell, there are a number of functions that I created for you that are the function to create the representations that you have seen in the slides. So the block sphere, the couple of block spheres, the bar plot, and probably also the Q sphere. No. Okay, and then we start, okay? So we are doing the same that you have just seen on the slides. So in order to create a qubit, okay, a qubit does not exist without a quantum circuit. So you create a quantum circuit with a single qubit, okay, and you have your qubit. Then a quantum circuit draw with matplotlib, and you have this representation. Then, starting from the quantum circuit, you can plot the block sphere, or you can plot the histogram. Basically, here you get the probability distribution of the results, and with this other function, you plot the histogram that you saw. So here, come on. I forgot to execute the definition of the function. Okay. QC is not defined. Okay, if you run them in sequence, it should be fine. So basically here you created a block sphere and the probability bar plot, and you get and here you plot the block sphere with this object, and with this displaying this object you display the bar plot. And in this other way, you draw in LaTeX the state of the system, which is a single qubit in state 0, so it's 0. Okay, so with these tools now you can play around and see what happens when you change the state of the system with some operators. So the exercise 1 suggests you to use the gate X, so QCX, on the only qubit that you have, so the 0, 1, to get the state 1. Okay, So the point of the exercise is create a single qubit circuit, apply the operator is written here how to do it, and third instruction, display the block sphere and the histogram. Okay. So I let you play around with it. So starting from here, the quantum circuit is the same. It's a circuit with one qubit. Okay. To this circuit, you need to apply the X operator to the qubit 0. So you simply write this command here, qc.c applied to 0. And then you again plot everything. If you need some help, raise your hand, I will be there.
Are the notebooks available anywhere other than the Google Drive? Because it's just
Okay, you can.
they're blocked on my work laptop.
Okay, you can download them.
From where?
Are you in the Slack?
No.
Okay.
I mean, is there are they like on a GitHub repo or?
Okay. If you download them, okay, I can send you via email the link if you want. No problem. But if you download them, you need to have an environment and to install the version of the packages.
That's fine.
Okay.
Yeah.
Did you want the link?
Yeah. I mean, could you rather than link, could you just email me the notebooks directly and I'll
Yeah.
And yeah, I mean, I can send the environment. So that's not a problem.
Okay.
Yeah.
It's
Shall I just add in?
you can. It's a US keyboard. Okay. Just send it.
So I think what I suppose I'm saying. So Google Drive is blocked. So
Okay.
like,
Okay.
yeah.
But because this is work.
Yeah, so,
Okay.
yeah,
No
yeah.
problem.
So,
No problem.
so
I think it's not that big. Download. No. Downloads. Okay, 0.5 megabyte, perfect. And voila. Anyone else need the notebooks? Okay. I should have sent it to you.
Yeah.
Okay. Yeah.
Operator, so the X operator flips the bit, right?
Yes.
And the Hadamard like does something in the middle, right?
Yes, exactly.
And tweaks the phase also, like changes the phase.
Not the Hadamard, but there are another operator. I think you will find it in exercise. Okay. For example, in the 1.4, you have rotations. So basically, the X rotates of pi radians, and Y, RZ, and Rx rotates on a specific angle. And these are the same commands I did to create the slides. So you have the.
What intuition should I have behind the phase? What is the difference when I have this? Let's say I have this arrow here on the equator and then here on the equator. Is there a difference between those two states?
Okay, the two states are different.
Okay,
so when two or more qubits interact each other, they take in consideration the phase.
Okay.
So they are two different states, and you can encode the information in those different states. But when you measure, you lose this information. And mathematically, this happens because when you squared the number, you lose some information, and you lose phase, exactly.
Okay, so are the two qubits that are the states in different phases, they can't interfere with each other, right? Or not?
Yes. Yes. And they are two. So when you measure the information in the quantum system, you change something.
Yes.
Okay. So during the circuit, you usually don't measure anything. Okay. You wait the end. Okay. So when you stay in the quantum world, so you don't measure, okay, you can use all the information, phase included. When you measure, you lose this information. So you need to create your quantum circuit to extract of the function that you are mapped in the quantum, not a single point property, but a global property. That's the point of creating a quantum circuit. And you can use internally all these huge number of configurations.
And what is the point to think like the qubits into the superposition? Like, what is the can say?
Okay, the most important part in creating superposition. What do you mean?
Like, why you do this? What is the reason to put it?
The point is that the quantum computer, the quantum mechanics works in this way.
Okay.
So you need to exploit that property for your usage. So the point is that you are seeing to it the kind of programming is completely different. You need to rethink any algorithm in a different way, because
so where are those? Because at the beginning you said that there are a number of states that can be represented. How is this a finite number of states? Like, is it a discrete number of states?
No, this is an infinite number of states, because the numbers are like reals. They are, but this is an infinite number of states. It is a finite number of basis states, depending on the number of qubits you are using. But when I show also plus and minus, this is another basis for which each one of the states is.
So 2 qubits can generate like 4 states to the power of 2, right? And 3 qubits like to the power of 3.
Exactly. And that's why in the molecule of caffeine you saw 2 to the power of 160. That's the point. Exactly. And the fact that you entangle the qubits, and you need that the qubit must be entangled, is because you can write any possible combination, linear combination, of that 2 to the power of n number of states.
And if you measure in entangled state, you measure 1 qubit, then do you lose the phase information in the other or not? You can still you can exploit this.
If they are you consume part of the information. It's not said that you consume it all. In the cases you've seen, you consume it all. Because
like this entanglement, and you just get the information from the one particle, is that you are destroying the entanglement? Like, this is not the case.
no,
So
the,
if you have like system,
the entanglement is destroyed if the particle interacts with another particle.
So
you make a measurement.
Or no, if you make a measurement, the entangle is destroyed, yes, but you are conditioning the state of the other. So you are using the entanglement, not destroying it. You destroy the entanglement with noise. You know that computers are kept to very low temperature in order not to other photons to distract the entanglement state. I have 20 minutes, right?
About 15.
15, okay. So, does it work? So I think the exercises are guided enough for you to reconstruct all we did. The first notebook is on a single qubit. The second notebook is on a system of more than 1 qubit, 2 and 1 case of 3. The third notebook is a very simple example how with a circuit you can create a classical logic gate, but the point is not building a logic gate with a quantum computer, because this proves that it's possible, but it's not convenient because you don't gain any speed or performance. The fourth one is the one on what I would like to focus now your attention, and it's split in two parts. The first part is still run on a simulator. Okay, and propose you two ways of using a quantum circuit. So basically, once you have created a circuit, okay, so before we saw this part of the circuit, now you can add these two gates that are basically measurements, okay? This gate here means measure the state of qubit 0 and write the information on the classical bit, on the classical wire 0, in the position 0. So you're getting the information from the quantum world to the classical one. And okay, and this example uses a sampler. So basically, you create, so you have your circuit created as we did before. You create a Qiskit runtime service, so a runtime, an executor of the circuit, okay, something that can run the circuit. Channel local means I want to run it on this computer, okay, which is classical, unfortunately. And so I must use a simulator. And this is the backend. I create a sampler with the backend. I run the circuit with the sampler, and I get as a result, okay, so you remember this is the circuit, okay, which was 50% 0, 0 and 50% 1, 1, okay? And if we measure 1, it can happen, it is 0, 0 or 1, 1, okay? And you don't have a lot of information about where the arrow is. Here you run this circuit with the sampler almost 1,000 times, and for each you list what you measure. So you measured 1, 1 509 times, and you measure 0, 0 515 times, okay? And you can easily calculate the probability. It means 49% 1, 1 and 50% 0, 0, okay? This allows us to know that the state was on the equator because we have 50% probability, okay? So this is how you extract information from the result of a quantum circuit. You simply try it 1,000 times, or less or more, okay, and you get conclusion from that. Okay, another way is the estimator, which in the end provides you, how can I say, a result of some observables. So basically you have a distribution, okay? You can apply some operator to the state, 0, 0 or 1, 1, and you get some numerical results, okay? And you can see what is the average value of that result, the observable, based on the state, the final state of your system. So you get a sort of the average of the possible result. Is another way to use it. Then here there is another nice exercise to create this GHZ state with n qubits. So basically you see here with 3 qubits, we have these entangled states of 2 qubits, 3 qubits. So entanglement happen not to be a property of 2 qubits, but of n qubits.
Might just be being redundant, but the charge above, it kind of looks like it goes below zero. So maybe that just maybe redundant, or there'd be a reason why it goes below zero.
The graphs are the same, but you need to cover all the possible states that you have here.
But how would you go if you scroll up to the charge? So that one there, where you've got the 0 line, it actually goes
Okay.
below that. And I'm not sure if that's just me being.
Actually, here I have a short time to explain it, but these are not 0011, okay? These are a set of operations applied to those states, okay? And this is the result of the value applied to the distribution. So it's a sort of, I have a distribution. I know that 50% of time happens to be 0, 0. Let's say 70% time 0, 0, 30% time 1, 1. 0, 0 with these operators result in 1. In the other case, result 0. The average is 0.7. Okay, it's so upon that distribution, you calculate a value of something. That can be, for example, in physics, the energy of the system. Okay. And you get back not the distribution, but the average value based on the distribution. Okay, and more interesting can be how to run the circuits on a real hardware. So here in prepare runtime service, okay, we need not only the code here, but also another ingredient. It's very simple. You need to go on the link that I don't find, of course. Okay, on this link here. This is one of my accounts. Okay, for free, here you can create a user, okay? And when you enter in the homepage of quantum.ibm.com, here you have an API token. This is the authentication key for you to access to the cloud of IBM, okay? And here you see that you have for free, okay, this is an account created just for the presentation, you have remaining 10 minutes each month to run your circuits. So you can try 10 minutes a month for free. Of course, you usually use the simulators. When you want to see a real quantum hardware, you use the cloud. Okay, and how this works, so we have a secret here. The secret is the token. And in this part of the code, you see that user data get Qiskit IBM token. In order to create this secret, okay, you copy and paste the token here, you can. Otherwise, what you do is go on this key, add a new secret, okay? In the value, you add Qiskit. Come on. Qiskit IBM token, and here you write, you copy and paste the token. Okay, it's the collab way to keep your secrets with your users and not with the notebook. I already have one here enabled. Okay, so I don't need this. So basically, I repeat, you go here, no, not here. You go here, okay, you create a user for free. You grab this token here, you copy the token, and you have 10 minutes to use your quantum computer. And you go in this part here, remote execution. Okay, this function basically creates a circuit with the 10 qubits in this entangled state. And here you have Qiskit runtime service that is imported for the other package. Save account. Token is the token taken from here. Okay. Channel IBM Quantum. Overwrite true, so you are sure that if there is already a configuration file, you are overwriting it, so no problem. And in this way, you have a configuration file with the token inside your virtual machine, your computer, whatever. And then you give a backend name, you create a Qiskit runtime service using this backend name, and you have a further step. Okay, when you go on a real hardware, okay, the real hardware not necessarily have another math gate. Okay, because at low level, it has a set of operations that are not all the operation available. Okay, when you code Python, there is no instruction in the CPU that is print. Okay, there are a sequence of operation to allow you to print or to do a sum. Time. Okay, thank you. Okay, so basically what you need to do is transpile your circuit. Transpile means create a circuit that will run on the hardware. And so this is my circuit, okay, the logic one if you want, and this is the transpiled one. Okay, you see that there are other operators. These are base operators for that hardware. Okay, and you here see 10 qubits, but actually I put false to the other qubits because this ISA circuit is the exact circuit that you will run on the final hardware. So this hardware has 128 qubits. If I put here true, I will see all the qubits, so 128 qubits, but the others will be empty, idle, not used. Okay, so the point of transpiling is changing your circuit in an ISA circuit. An ISA circuit is a circuit that has as gates as the gates that exist in the hardware and all the qubits that the hardware has. Okay, it's a sort of compilation. So you have your C code, you compile it, and you run on PC. But you need to compile differently to run on an embedded device, for example. The same code to different binary code. Here, the ISA circuit is like the binary code. Okay, it's the assembler of the quantum computer. And here we do the same thing with an estimator. We are running the estimator on the real hardware. And if you run this, you arrive here. I could do right now, but I don't know if I have time. I will try. Okay, when you arrive here, the job is sent to the cloud, but not executed instantly. Okay, it will be put in a queue. Okay, you will wait, I don't know, 40 minutes, 1 hour, 3 hours, 6 hours, it depends. And you will see your task here, okay, waiting. It will give you a time to wait. Now let's see if this happens. Okay, and what remains to you is the job ID. Okay, so you close your computer, you go to have a coffee or a dinner, and come back. And what you do is, I'm lost. Okay, you set your old job ID, and you do your analysis. Okay, that's the idea. Let's see if not yet. Okay, but the notebook works. I tried it a lot. So now time is up, but you can try it. Okay, I hope you enjoyed the workshop. If you have questions, I'm here, and that's it. Thank you.